Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Alpesh Dafda, and in this video class we will study image sensing and acquisition. So as usual, starting with the name, what is the meaning of sensing? Sensing means to perceive or to grasp, right? And what is the meaning of acquisition? Acquisition means to obtain, to acquire, right? So image sensing and acquisition means to perceive or grasp the image and obtain it for digital image processing, right? Image sensing and acquisition will always be the very first stage or very first step in digital image processing, and hence it is very important. Okay, so let us start. So we always do sensing using by some sensor or camera, right? And this sensor is nothing but a transducer. Okay, it will be converting the light energy into electrical energy, because we can perform processing on electrical signals, and these electrical signals of course will be converting into digital signals by using some digitizer or analog to digital converter. So sensor is basically a transducer that will be converting the light energy into electrical energy, right? Image sensing is done by a sensor when it is illuminated by either reflected or transmitted energy from the object or picture under consideration. So in the process of acquisition, there are three components. Number one is illumination or the light energy. As you can see here, the light energy is radiated by the energy source. The optical system or the lens system of the camera, right? This is the second important component. And third important component, and very important component, is the sensor itself, right? So you can see here that the energy is falling on this particular object and the light is reflected from this object. That light is falling on this particular lens. The lens passes it to image sensor, where the image is sensed or perceived. Okay, so the illumination may be either from a light source or from a source of electromagnetic energy such as radar, infrared or X-ray energy. So depending on the nature of the source, the illumination energy is reflected from or transmitted through the objects. To focus the reflected or transmitted energy, certain lens or mirror system is always required. This is called the optical system. In some situations, the radiation is focused onto a photo converter, for example a phosphor screen, which converts the energy into visible light. Electron microscopy and some applications of gamma imaging use this approach. So the important part of image acquisition is the image sensor. The light reflected from the object must be recorded, and this is done by an image sensor. An image sensor consists of 2D array of cells, and each of these cells is denoted as a pixel and is capable of measuring the amount of incident light and convert that into a voltage, which in turn is converted into a digital number by a digitizer or an analog to digital converter. Actually, the image sensor is a part of digital camera. So before a camera captures an image, all the cells are emptied, meaning that there are no charges present. When the camera captures an image, light is allowed to enter and charges each cell. After a certain amount of time, known as exposure time, which is controlled by the shutter, the incident light is shut out again. If the exposure time is too low, the result is an underexposed picture, or if the time is too high, it forms overexposed image. Getting it, right? Let's go ahead. So figure 1, 2 and 3 shows the three principal sensor arrangements used to transform illumination energy into digital images. In this case, the incoming energy is transformed into a voltage by the combination of input electrical power and sensor material that is responsible to the particular type of energy being detected. The output voltage waveform is the response of the sensor, and digital quantity is obtained from each sensor by digitizing its response. So there can be three principal arrangements: a single sensor like this, a line sensor which is a line of single sensors, and an array sensor which forms a grid or a matrix of single sensors, right? Very first, let us understand the image acquisition using a single sensor. So a single sensor is the simplest among all the image acquisition sensors. This figure shows a single sensor. The best example of this single sensor is a photodiode, which is constructed from silicon material whose output voltage waveform is proportional to the incident light. So you know how this photodiode works. See, for this example, the light source is emitting the light that is detected by the photodiode. The light beam is falling on the photodiode, right? And this can be kept on a doorway. So if no person is passing or no particle is passing, then the light is detected by the photodiode. But when some person passes through this doorway or cuts this beam of light, at that time the light falling on the photodiode cuts off, and hence you can beep a alarm. So in this way, photodiode is used to detect the light. So the use of this filter in front of the sensor improves the selectivity. For example, a red pass filter in front of this light sensor allows only red light. As a consequence, the sensor output will be stronger for the red light than for other components in the visible spectrum. So the output voltage waveform will be generated like this. So in order to generate a 2D image using a single sensor, there has to be relative displacements in both X and Y direction between the sensor and the area to be imaged. So this figure shows an arrangement used in high precision scanning where a film negative is mounted onto a drum whose mechanical rotation provides displacement in one dimension. The single sensor is mounted on the lead screw that provides motion in the perpendicular direction. Since mechanical motion can be controlled with high precision, this method is an inexpensive but slow way to obtain a high resolution images, right? Other similar mechanical arrangement use a flat bed with a sensor moving in two linear directions. These types of mechanical digitizers sometimes are referred to as micro densitometers. So one relative displacement is in the X direction like this, and in the Y direction displacement is obtained by the rotation of this drum. So let's go ahead and understand the image acquisition using line sensor or sensor strips. Okay, sensor strip means a line sensor like this. So sensor strip consists of an inline arrangement of sensors in the form of sensor strip, and it is more widely used than a single sensor. The strip provides imaging elements in one direction. Motion perpendicular to the strip provides imaging in the other direction, as shown in figure over here, right? And this type of arrangement is used in most flatbed scanners like this. Okay, so line array will be moving in this particular direction and the image will be scanned. So sensing devices with 4000 or more inline sensors are used. Inline sensors are used routinely in airborne imaging applications in which imaging system is mounted on an aircraft that flies at a constant altitude and speed over the geographical area to be imaged. One-dimensional imaging strips that respond to various bands of electromagnetic spectrum are mounted perpendicular to the direction of flight. So the imaging strip gives one line of an image at a time, and the motion of the strip completes the other dimension of a two-dimensional image. Lenses are used to project the area to be scanned onto the sensors. So the sensor strip can also be used for image acquisition using a circular sensor strip. The sensor strips mounted in a ring configuration are used in medical and industrial imaging to obtain cross-sectional slices or images of 3D objects. A rotating X-ray provides illumination, and the portion of the sensors opposite the source collect the X-ray energy that passes through the object. So this X-ray is rotating and it will be captured by the sensor over here. And obviously the sensors have to be sensitive to the X-ray energy for this particular application. And this is the basis for medical and industrial computerized axial tomography imaging or CAT imaging, right? There will be linear motion of this 3D object, and number of slices of such images will be obtained which are processed later for medical applications, right? So that is also one of the important application of sensor strip, right? Let's go ahead and understand the image acquisition using sensor array or array sensor. So this type of arrangement is formed in digital cameras. A typical sensor for this camera is a CCD array or a charge coupled device array, which can be manufactured with a broad range of sensing properties and can be packaged in rugged arrays of 4000 cross 4000 elements or more. CCD arrays are used widely in digital cameras and other light sensing instruments. The response of each sensor is proportional to the integral of the light energy projected onto the surface of the sensor, a property that is used in astronomical and other applications requiring low noise images. So the first function performed by the imaging element is to collect the incoming energy and focus it onto the image plane. If the illumination is light, the front end of the imaging system is a lens which provides the viewed scene onto the lens focal plane. The image array, which is coincident with focal plane, provides output proportional to the integral of light received at each sensor, and a digital or pixel image is formed on the array sensor like this. So this is the actual element. The light is reflected from this actual object and is falling on the image plane, and further it is converted into digital image using pixels like this. This is a typical CCD array which is consisting of 2184 cross 1472 pixel, and pixel size is approximately 6.8 micron square for this particular CCD array. Okay, so this is how the image acquisition is done by using the single sensor, line sensor and the array sensor. Now let us understand a simple image formation model. See, a image is defined by two-dimensional function f of xy, as we saw in the very first lecture. The value or amplitude of f at spatial coordinates x, y is a positive scalar quantity. When an image is generated from a physical process, its values are proportional to energy radiated by the physical source. Okay, so as a consequence, f of xy must be non-zero and finite. That means f of xy should be in between 0 to infinite. The function f of xy may be characterized by two components: the amount of source illumination incident on the scene being viewed and the amount of illumination reflected by the objects in the scene. So these are the illumination and reflectance components denoted by I of xy and R of xy, right? That is illumination component and reflectance component. So these two functions combine as product to form f of xy. So f of xy is equal to I of xy into R of xy, where I of xy is in between 0 to infinite and R of xy is in between 0 to 1. Okay, so R of xy is equal to 0 means total absorption, right? And R of xy is equal to 1 means total reflectance, right? So we call the intensity of a monochromatic image at any coordinates xy the gray level L of a image at that particular point. That is L is equal to f of x comma y, right? For a 8-bit image, L will be 256. So the interval of L ranges from 0 to L minus 1, okay, where L is equal to 0 indicates black, okay, and L is equal to 1 indicates the white, right? All the intermediate values are shades of gray varying from black to white, right? So this simple image formation model can be seen in the previous slide. So this one is a simple image formation model, right? So remember, for this image, x are the values of different rows, y are the coordinate values of different columns, and f is the intensity value of that particular pixel, right? So for digital image processing, the image is made up of pixels. And what is pixel? Pixel is any of the very small individual area on a computer screen or sensor which together form the whole image. So smallest discriminable area in a digital image is called a pixel. So in digital imaging, a pixel or PEL or picture element is the smallest addressable element in the image or smallest discriminable element of a digital image. Okay. So that is all for this video class. In the next video class, we will understand different relationship between pixels. Thank you very much.